Thanks for letting me talk today. Go to the next slide. I wasn't quite sure what to say to this audience in terms of, ISRU and what type of research we would do on the lunar surface. Can you advance to the next slide, please? So thank you. So I'm going to talk a little bit about lunar ISRU and what we see going on in the next decade, and then what kind of ISRU relevant biological and physical sciences research activities might benefit ISRU on the lunar surface itself. I noticed other people pointing to, gaps and Moon to Mars objectives. I have that information in other presentations, but did not think it would be, needed here, but I can always provide that at some future date. So if you go to the next chart, I'm going to talk a little bit about what is ISRU and how does it fit into the architecture? What are some of the things that we're thinking about? So if you go to the next chart, we like to basically provide an overview whenever we give a discussion on what is in situ resource utilization. We like to say it's everything from prospect to product. It involves hardware and operations that can harness and utilize in situ resources to create commodities, and that could be for either robotic or human exploration missions and eventual space commercialization. I put in situ in kind of brackets because we normally think of the regolith, the sun, the vacuum, the volatiles, but we also consider trash and discarded hardware as in situ resources as well. And we talk about commodities because these are things that we eventually think we're going to sell so that there'll be a supply and demand commercial effort. So when you think of the prospect to product chain, it starts with destination reconnaissance and resource assessment. You need to know what's there, the physical, mineral, chemical, volatile aspects, thermal resistance, electrical properties, things like that, as well as the terrain and the geological context in which all those materials are found. Once you think you know what the resource is and it's been mapped and located, you then start to think about, well, how am I going to acquire it? And how might I isolate and prepare certain aspects of that resource? So instead of having bulk regolith, maybe I size sort it, maybe I crush it, maybe I separate out certain minerals. Same thing with atmospheres, the Mars atmosphere. Maybe I pull out, this carbon dioxide or the nitrogen, something like that. Once you've acquired that resource and prepared it, you can then go into processing. That could be chemical, thermal, electrical, and now we're starting to really think about biological processing. And there are two kind of subsets to this. One is the mission consumables, the waters, the propellants, the life support commodities and consumables, things like that. And then how do we support construction and manufacturing? A particular subset that we like to focus on is water, whether it's on the moon, Mars, or asteroids. Water as a resource in a product and something that you can process provides tremendous benefit. Two aspects to always think about. ISRU and where I come into it is there's a lot of technical disciplines that have to come together to make ISRU work. It's not just the chemical processing. There's excavation, there's autonomy, there's power, there's cryogenic liquids and such. So you have to make sure all of those are aligned. The other is that ISRU does not exist on its own. By definition, it must provide a product to a customer. So the architecture has to be aligned with using those products. Next chart. This chart, again, I think you'll have access to all of these. We break down those categories into subcategories so that we can put out solicitations and define what our research and technology development needs are. We have a cross-cutting area that deals with both simulants and planetary environment test capabilities. And then we actually look at it from a flow diagram perspective as well, because as you're flowing the materials, as you're flowing the resources and such from one box to the next, decisions you make in one of those boxes will strongly influence the upstream and downstream technologies that you use and the processes that you select. Next chart. This is just, again, a brief list of some of those commodities, water being one of the most important on the moon. We hope to find that in the permanently shadowed regions and craters at the poles. Oxygen and metals from regolith. There's both highland and mare type regolith. Both of them have approximately 40 to 45% oxygen, as part of different minerals. The highland regolith has a lot of aluminum and silicon, whereas the mare allows you to have more iron and titanium. There's propellants that we eventually want to make. There's manufacturing and construction feedstocks, and we're starting to try to consider foods and nutrients and plant growth support activities as well. Next chart. Why do we do ISRU? I'm, again, not going to spend a lot of time, but there's a lot of benefits. Typically, the most important one is mass and cost reduction over time. I like to say if you're doing a camping trip, you don't need ISRU, but if you plan on going there for any particular amount of time, you're not going to want to constantly bring everything with you. You're going to want to start using items, just like if you stay at a cabin or build a cabin and such. By being able to make things where you're at versus waiting for replacement parts from Earth, you start getting into crew safety and mission success aspects. By not having to bring everything with you, you can start thinking about new types of missions that you couldn't before. And then a lot of what we hope to do on the moon and Mars spins back to Earth and vice versa with respect to renewable energy, recycling, CO2 reduction, water aspects, environmentally friendly mining and construction, things like that. Next chart. So we have a resource interest as well as a time phasing of both the locations and the resources and the type of commodities. We're starting at the South Pole. As I mentioned, the highland regolith has a lot of oxygen, aluminum, and silicon to it, and we hope to find water and other volatiles in the permanently shadowed craters. Over time, as we start going more equatorial to mare locations, the ilmenite, the pyroclastic glasses give us some iron and titanium that you really can't find at the poles, and then maybe even rare earth elements and radioactive elements like thorium and uranium. And on the right side, I kind of list, starting out, we just, water, oxygen, and even just using regolith for shielding and berm building is provides really immediate support. And then over time, we'll start refining that more and more. And so you try to have the minimum infrastructure to begin with, the easiest stuff to mine, and a product that can provide almost immediate benefit. And then over time, you expand on those. Next chart. From a time phasing point of view, looking at the moon, there's kind of two major resources I've kind of fleshed out a little bit. What's in the permanently shadowed crater, the water and the L-cross volatiles, and then what's in the regolith, the oxygen and the metals. We're pursuing both paths in parallel with the idea that we will eventually build what's called at least one pilot plant. And so the idea is on the top, looking for water. Where is it? How is it distributed? Some missions have failed. I put a question mark on Viper because that was a very important mission for us that was recently canceled, and there's an RFI out on the street on what to do with that mission. The internationals are performing some missions to look for water, but will we learn enough to locate it and mine it? That's still a big question mark. We do know a lot about regolith on the moon, can always learn more, but we're looking at some kind of demonstrations on how you would collect it and process it into oxygen and metals, with the idea that a pilot plant is an end-to-end demo at a scale that eliminates the risk of going bigger and providing a commercial product. So that's our goal sometime in the 2030s. Next chart. And so this goes again to the philosophy where, if you look at the early Artemis missions and Apollo missions, pretty much they were camping trips. You brought all your food and water, you brought your shelter, you brought your energy, and you basically have some minimal transportation capabilities. But if you're going to stay, you change what you bring. You learn how to use the resources around you for food, water, shelter, energy, and how to best support and grow your transportation systems. So that's kind of our goal for sustained lunar evolution. Next chart. So I'm going to talk a little bit about now what kind of research might be done from both the biological and physical aspect. We plan on doing a lot of stuff on Earth, obviously, and using microgravity and low G spacecraft and airplanes. But what would going on the lunar surface give us? So if you go to the next chart, we have identified what the challenges are with respect to ISRU from a resource understanding, from an operational aspect, from a technology aspect, and from an integration aspect. And so I started to identify, what are those research aspects, uncertainties with the resources, operating in extreme environments, the impact of low and microgravity, and how you might maintain all of this. Next chart. And so we looked at those challenges. The bottom chart basically starts saying, well, where would I address those challenges the most? In some cases, we basically say you need to do that at your site of exploration, that simulants and environmental chambers and gravity offloading and 30 seconds or 3 minutes of lunar gravity aren't enough to really get to the knowledge base that you want. So on the right hand side, we talk about the terrestrial research that we're doing. We really need good simulants and environmental chambers, but the lunar surface activities will allow you to really dive into those challenges and risks to fully understand the implications of the regolith and the lunar environment, and that you just can't get from simulants. And it could help basically provide a layer of understanding that you just can't get from doing a demonstration. So next chart. So the next two charts basically go a little bit more into that. So on the right-hand side, these are the type of operations that we need to do on a day by, round the clock basis. We'll need granular flow for excavation and transfer of regolith, and size sorting, separation of the different minerals through different techniques like electrostatics, turbocharging, magnetic, and a number of different factors. Now getting into the processing from a gas solid perspective or a liquid solid perspective, even going into the molten range. And then, I have gas liquid and liquid processing from both a chemical and a biological perspective. So then when you go to the left-hand side, you look at, well, there's significant aspects associated with low G and microgravity for solids and liquids. You start thinking about your ISRU operations and how, terrestrial simulants and Earth gravity, affect what you're doing. And then if you go to the next chart, which is, I think, my last one, you start thinking about now the severe environments. Somebody brought up radiation, previously. So, that charges the and it influences the surface material, as well as it will impact any of the biological processing systems that we're thinking of. And then vacuum operations and exposure and such. Next chart. And I think, so there's takeaways. There's a large number of challenges. We have gaps. Recently, we put out a shortfall list, and the top 4 shortfalls for ISRU pretty much fall into the how do you find the water, how do you mine water, how do you extract oxygen and metals, and how do you make propellants. So everything that I mentioned so far pretty much falls into the top STMD priorities for ISRU. And then I highlight again the biological and physical sciences on the lunar surface could be extremely helpful in understanding the very small nuances as we evolve ISRU from demos to initial commercial products to larger scales. And with that, I'll come to a close. Thank you.